In a high concurrency environment, the precision of your teardown determines whether your application remains stable or suffers a resource leak. The difficulty isn't in opening a connection, it's in ensuring that connection returns to the pool the moment the work is done. Imagine a high-traffic database pool. Every microsecond a connection sits idle outside that pool, it starves every other part of your system. You have to return that resource the millisecond your asynchronous operation finishes. For years, Swift developers used the defer block to handle this cleanup. But until Swift 6.4, the compiler prevented the use of the await keyword inside a defer scope. This meant that if your cleanup required its own asynchronous call, like releasing a pooled connection, you couldn't use the language's native safety mechanisms. You had to step outside the structured concurrency model and rely on architectural workarounds. This is the standard workaround. You check out a connection, do work, and spawn a task.detached block strictly to handle the teardown. Calling detached severs the cleanup operation from the original function stack frame. The function finishes, the frame collapses, and the cleanup is left floating in the background. That floating task now runs whenever the runtime scheduler gets around to it. The connection might not return to the pool for several milliseconds, even as the next caller is already requesting it. If the cleanup itself fails or throws an error, that error is lost. Detached tasks are fire and forget. The system has no way to report that the connection was never actually returned. Relying on unstructured tasks for resource teardown removes the deterministic nature of memory lifetimes. Under heavy load, this leads to untraceable concurrency leaks. Swift 6.4 introduces SE0493, which allows await inside defer blocks within any asynchronous function. When the function reaches its exit, the defer block locks onto the stack frame's bottom boundary. Instead of severing the cleanup, the frame merges it into its own lifetime. Control returns to the parent only after the connection is pooled and the frame dissolves. Asynchronous resource teardown is now tied directly to the function's lexical scope, restoring the lifetime guarantees that unstructured tasks destroyed. However, this update reveals a conflict between execution scope and task state. Asynchronous defer guarantees that the cleanup runs, but it also inherits the parent task's cancellation signal. In this tree, if a parent task is canceled, that signal cascades down the branches directly into the asynchronous defer block. Because Swift uses cooperative cancellation, any await instantly aborts. The cleanup logic stops, leaving the connection dangling. The developer expects the defer block to save them, but the cancellation signal skips the exact teardown it was supposed to perform. To solve this, Swift 6.4 adds SE0504 task cancellation shields. A cancellation shield enforces a non-cancelled state strictly for the duration of its closure. As the red cancellation signal hits the shielded node, it deflects, allowing the cleanup code to run to completion, regardless of the parent state. The rule for system architects is clear. If an asynchronous teardown must reach an external resource to prevent a leak, that async defer must be wrapped in a cancellation shield. We have secured the cleanup, but we also need to control the trigger. Traditionally, developers limited execution by racing a network call against task.sleep. This reveals the problem of stack drift. When you pass relative sleep durations down a call stack, you accumulate latency at every layer because of thread scheduling overhead. SE0526 introduces withDeadline. Instead of counting relative seconds, it uses an absolute continuous clock instant. Because this instant is absolute, nested calls resolve to the earliest expiration point. This removes the need to manually calculate remaining time at every layer. When the clock hits that instant, the runtime triggers a cancellation error with a specific .deadline expired reason. These absolute deadlines create a drift-free cancellation hierarchy, providing the precise trigger for the shielded async defer sequence. Now, Swift 6.4 enforces these patterns at the compiler level, targeting unstructured leaks. Previously, it was common to initialize a task that could throw an error and then ignore the result, effectively masking lost connections and failed cleanups. Under SE0520, the compiler now issues a warning if you ignore the result of a throwing task initializer. This forces you to handle the error, ensuring that a deadline expiration or a network failure is actually observed by your code. Finally, SE0518 adds the sendable annotation, letting you explicitly mark types that must not cross concurrency boundaries. These markers close the final loopholes in the system. They ensure that a developer cannot accidentally bypass the strict boundaries defined by the architecture. We can now combine these updates into a single, reliable operation. The first layer is the boundary, the absolute time limit set by withDeadline. The second layer is the core business logic, awaiting data from the network. And the third layer is the guarantee, the teardown sequence, where async defer and the cancellation shield interlock to ensure the resource is reclaimed. We have replaced a collection of drift-prone hacks with a compiler-enforced hierarchy. These features shift the burden of safety from the developer to the language itself. By coupling memory lifetimes, time bounds, and teardown logic, Swift 6.4 provides a verifiable path for every resource your application touches. By mastering these boundaries, you can build high concurrency systems that remain stable and predictable, no matter how the external environment fluctuates.